Hello and welcome to this IEA Clean Coal Centre webinar. My name is Nicol and today's webinar is called Application and Development Prospects of Double-reheat Coal-Fired Units. This webinar is based on my report of the same title. Reports can be downloaded free of charge by residents of member countries or employees of sponsoring organisations of the IEA Clean Coal Centre, or within 6 months after publication. Reports are freely available to all. If you have any questions during this webinar, or indeed any comments, please click on the question button on the top of your screen, type the question in, and I will answer the questions at the end. So I will now review and analyse the technical and economic performance of operational and decommissioned coal, oil and gas-fired double reheat units globally. Then I will move on to recent technical developments and advances in turbines, boiler configuration and steam cycles, with an evaluation of double reheat units that are currently in planning and under construction. The final slides will review the prospects for double reheat steam cycles in advanced ultrasupercritical coal-fired power units. From the 1880s to the 1950s, pulverised coal-fired power plant employed a single circuit of steam through the boiler and the turbine. In the early 1950s, the single reheat loop was established and has become the standard cycle. The extra steam loop takes steam from the high-pressure turbine module and reheats it in the boiler before returning it to the intermediate pressure turbine module. In the late 1950s, double reheat cycles were introduced alongside the early supercritical boilers. The double reheat cycle adds another steam reheat loop to the single reheat cycle, which can require an additional turbine module. Adding a reheat steam loop increases the electrical efficiency by increasing the average temperature of the steam cycle. Today, single reheat steam cycles are common. Double reheat steam cycles are rare, and there are no triple reheat cycles, as this is the point of diminishing returns. Germany was the first country to employ double reheat steam cycle technology. 11 gas and coal-fired double reheat units were commissioned in Germany between 1956 and 1982. Amounting to 1.64 gigawatts. This graph is a plot of the electrical efficiency and unit size with year of commissioning for coal-fired units only. The unit size increased from 100 to 475 megawatts, and the electrical efficiency almost reached 40%. All efficiencies I mention in this webinar are net electrical efficiencies on a lower heating value basis for coal, unless stated otherwise. The boiler and turbine manufacturers were mostly German, with Siemens, EVT Energy and Verfahrens Technik. The American company ABB Power Generation also manufactured some turbines. The first double reheat unit, Hull's Unit 1, had very high superheat temperature and pressures of 600 degrees Celsius and 30 megapascals respectively. Over the next 26 years of development, these steam conditions settled on superheat steam at 530 degrees Celsius and 25 megapascals. The steam conditions were decreased because the new thick-section austenitic steels at the time were initially run too hot and suffered from excessive fatigue damage. Metallurgists initially thought that austenitic steels could be used for thick-section components at superheat temperatures up to 650 degrees Celsius, but this was not the case. A double reheat cycle has not been built in Germany since 1982. "32 double reheat units were built in the USA from 1957 to 1982, amounting to approximately 17 gigawatts. Of these units, 27 are hard coal-fired, 3 are gas-fired, and there is 1 oil-fired and 1 lignite-fired unit. This graph shows the electrical efficiency and unit size with year commissioned for all double reheat units in the USA. This graph shows the increase in unit size with year commissioned from 120 to 816 megawatts. The electrical efficiencies range from 27 to 40%. The graph shows that the efficiencies decreases slightly with time, but this is because the trend is skewed by the small and inefficient units that were the last to be commissioned. The US boiler and turbine manufacturers dominated the world market in the 1950s, 1960s and 1970s. Babcock and Wilcox manufactured most of the boilers, with Foster Wheeler and ABB Combustion Engineering manufacturing the remainder. General Electric dominated the turbine manufacturing, and Westinghouse Electric had a smaller share. The first coal-fired supercritical double reheat unit had high steam conditions. The superheat steam of Eddystone Unit 1 in 1959 was initially set high at 649 degrees Celsius and 34.5 megapascals. Numerous problems were encountered with such high temperature steels, and the availability of these units dropped, and the maintenance costs increased significantly. The only solution to these problems was to lower the steam conditions and derate the unit. These problems were entirely due to the inexperience with the use of austenitic steels at such high steam temperatures at the time, and was nothing to do with the double reheat cycle. The last 18 coal-fired double reheat units to be built in the USA had lower steam temperatures of 538 degrees Celsius and pressures of 24 megapascals. The operational record of double reheat units in the USA has since been excellent, with operational lifetimes greater than 50 years. It was calculated that the double reheat cycle increases efficiency by 1.5 to 2 percentage points above the single reheat cycle. The cost of building such units dropped from $170 per kilowatt to $100 per kilowatt in the 1960s. However, in the 1970s, the cost of building coal-fired power plants increased, largely because of the requirements for air pollution control and cooling towers. From the 1970s up until recently, no coal units were built in the USA because of a decreased electricity demand and an increasingly privatised electricity industry, which does not favour long-term investments. Most double reheat units will be decommissioned in the next few years or converted to firing gas or biomass due to more stringent emission regulations set by the Environmental Protection Agency. 11 oil and gas-fired double reheat units were built in Japan between 1968 and 1990, amounting to 7.2 gigawatts. The unit size gradually increased from 450 to 700 megawatts. Mitsubishi Heavy Industries manufactured boilers and turbines. Babcock Hitachi manufactured some boilers, and Toshiba manufactured some turbines. The steam conditions began modestly compared to similar units in the West. The first 9 units operated with superheat steam at 538 degrees Celsius and 24 megapascals, and Kawagoe Units 1 and 2 increased such parameters to 565 Celsius and 31 megapascals. The gas-fired units at Kawagoe could reach an impressive net electrical efficiency of 46.8%. Coal-fired double reheat units have not been built in Japan because they have not been economically favourable. Two double reheat units were built in Italy in the late 1960s, and 2 double reheat units were built in Denmark in the late 1990s. Both of these countries are net energy importers, which means they generally pay a higher price for fuel. Therefore, the fuel savings achieved with double reheat cycles is economically favourable. The double reheat coal-fired power plant unit in Denmark Nordirland Unit 3 is a combined heat and power station. The unit reaches 47.2% electrical efficiency in power-only mode, which is the highest in the world to this day, a record held for almost 17 years. When operating in combined heat and power mode, the unit converts 90% of the energy of coal into electric and to heat in district heating schemes. Double reheat technology was chosen not only for efficiency gain. The double reheat cycle has a higher condenser pressure, which eliminates the erosion of last stage turbine blades in the low pressure module caused by water droplets. Additionally, strong governmental and public forces for environmentally friendly and sustainable energy generation favoured double reheat technology in Denmark. Double reheat units emerged with the introduction of supercritical units in the 1950s. Most double reheat units were built around the 1960s and 1970s in Germany, the USA and Japan. Double reheat technology peaked in efficiency with Nordirland Unit 3 in Denmark. In total, 60 double reheat units were built, amounting to 27.9 gigawatts, 37 of which are coal-fired, amounting to 17.7 gigawatts. No other double reheat units have been built in the last 16 years. Over 94% of the boilers and turbines were manufactured in the same country they were commissioned in, which shows that if a country identifies double reheat as part of its energy portfolio going forwards, then it will generally develop the engineering and manufacturing skills to do so. Double reheat units became unfavourable from the 1970s onwards, largely due to the introduction of nuclear power and combined cycle gas turbines, and persistently low oil prices. Compared to a single reheat unit, double reheat units have an electrical efficiency increase of 0.8 to 2 percentage points, and the operational and maintenance costs are similar. Finally, most double reheat units will be decommissioned over the next few years. I will now look into the development prospects for double reheat units. Double reheat turbines are still available on the market. This slide shows a 1000 megawatt double reheat turbine by Siemens. This is a tandem compound single train turbine with 3 low pressure cylinders. Shanghai Turbine Works manufactures such turbines under foreign licenses. They supply a 660 megawatt and 1000 megawatt turbine with superheat steam at 600 degrees Celsius and 31 megapascals. Siemens are working on an advanced single train double reheat design which employs increased steam conditions, advanced sealing, an optimized cold end and improved steam cycle as shown here. The plant engineers at Dong Energy, who designed the double reheat units in Denmark, have devised and patented the master cycle. The master cycle modifies the steam cycle by adding a small turbine module separate to the main turbine, which can replace a boiler feed pump and reduces the size and amount of high temperature components. This process flow diagram shows the master cycle where the components in the green box are altered from a conventional double reheat cycle. Compared to a conventional double reheat cycle, the master cycle increases electrical efficiency by 0.5 percentage points and reduces capital costs. Dong Energy conducted a feasibility study for a third double reheat cycle, double reheat unit in Denmark in a series of Convoy units. This was an 800 megawatt coal-fired double reheat unit using the master cycle at ultrasupercritical conditions. However, in 2010, Dong Energy announced that they would reduce their carbon emissions, which has led to the decision not to invest in coal-fired power plants. Shanghai Turbine Works have developed the Echelon Cycle, which is similar to the master cycle. The Echelon Cycle can reduce the cost of a conventional ultrasupercritical double-reheat unit turbine, and the Echelon Cycle is planned to be demonstrated in China in 2017. Engineers at the Shanghai Waigaoqiao power generation company in China have developed a unit configuration called the cross-compound high-low position arrangement, or CCHLPA. The high pressure and intermediate pressure turbine modules are mounted at the same level as the outlets of the boiler steam headers, which is roughly around 80 to 85 metres above ground level, and the low pressure modules remains roughly above 17 metres above ground level in the conventional turbine house. This CCHLPA reduces the capital costs for units with high steam conditions through less use of expensive high temperature materials, and it also slightly increases the unit's efficiency. In China, from 2012 to 2020, 400 gigawatts of new coal power is planned. There is interest in double reheat technology for the following two reasons. Firstly, China has serious problems with air pollution. The Chinese government has enforced much lower emission standards for coal-fired power plants, and double reheat units can reduce such emissions. Secondly, with relatively high coal prices coupled with relatively low labour costs, double reheat ultrasupercritical units are seen as economically favourable. Therefore, double reheat technology has been recently identified as a key research and development project for China's 12th five-year plan. As shown in this table, 13 units are currently under construction, amounting to 11 gigawatts. The two coal-fired units at Guodian Taizhou will soon be the world's largest double reheat units at 1,000 megawatts each, and the most efficient, reaching 47.94% electrical efficiency. The single shaft tandem compound turbine manufactured by Shanghai Turbine Works has 10 stages of regenerative feed water heating, and the AUSC steam parameters have been achieved using commercial steels. The payback of the second reheat cycle is an additional 6.25 years on the single reheat cycle. Shanghai Turbine Works have recently reported that Guodian Taizhou was successfully operated at 3,000 revs per minute on the 4th of August this year during the first stages of commissioning. The Shanghai Waigaoqiao Power Generation Company are building Unit 9, which is planned to be commissioned in 2017. This unit is a double reheat cycle with the CCHLPA unit configuration as explained earlier. Unit 9 will have a 1,350 megawatt cross-compound ultrasupercritical turbine designed by Siemens and built in China. It is calculated to reach 48.92% net electrical efficiency, and the payback period is expected to be less than 5 years over a single reheat unit. The steel barrier presently lies at 620 degrees Celsius. Current research aims to use nickel alloys to reach 700 degrees Celsius superheated steam, known as Advanced Ultrasupercritical Technology, or AUSC, with a corresponding net electrical efficiency greater than 50%. There are national and international research collaborations in the USA, EU, China, Russia, India and Japan. Double reheat cycles combined with AUSC steam conditions could provide lucrative gains in electrical efficiency. When operating with 700 degrees Celsius superheat steam, double reheat cycles would increase the efficiency over single reheat cycles by plus 0.7 percentage points. In Europe, Burmester and Wayne Energy designed a 1,100 megawatt master cycle unit which could reach 52.2% net electrical efficiency on coastal sites with AUSC steam conditions. The Japanese program developed an AUSC double reheat program as shown on this slide here. In China, double reheat AUSC technology is under investigation. Such plant would employ the CCHLPA technology as described earlier to minimise the amount of pipework and could reach 52% net electrical efficiency. This is a scattergraph of the efficiency and unit size of all double reheat units built, planned with commissioning year. Assuming Guodian Taizhou in China is commissioned this year, for coal-fired double reheat units over the last 60 years, the electrical efficiency increased by almost 21%, by almost 21% from 27% to 47.94%. And the unit size has increased tenfold from 100 megawatts to 1,000 megawatts. This graph by Siemens shows the historic and projected efficiency increase between single and double reheat turbines. Siemens say that their current double reheat turbines can reach 48.8% efficiency, which should be demonstrated at Waigaoqiao Unit 9 in 2017. Applying AUSC technology to Waigaoqiao Unit 9 technology would allow such efficiency to reach 52%. This graph shows that AUSC double reheat units could exceed 52% efficiency and even reach 54%. To conclude, with operational experience in 5 countries over 60 years' time, double reheat technology is technically proven, it has no limitations, and they have been economically favourable over single reheat cycles due to the increase in electrical efficiency. The existing double reheat units in the developed countries will soon be decommissioned and no new builds are likely. Due to a combination of low labour costs, high fuel prices and increased demand for electricity, double reheat units are favourable in developing countries. Presently, there is rapid deployment of ultrasupercritical double reheat units in China, which will reach a record-breaking net electrical efficiency of 47.94% this year. Increasing costs associated with emitting carbon dioxide will favour double reheat technology in the coal industry. Improved steam cycles and unit configuration can increase efficiency to 48.82%, lower capital and running costs, and should be demonstrated in 2017. Finally, advanced ultrasupercritical technology using double reheat could reach 50% in 2021 and 54% in the 2030s. This webinar covers the main points of my report, but there is plenty more information and finer detail in the 81-page report, which can be found on the IEA Clean Coal Centre website. Thank you for listening, and I'll now welcome any questions. I've got one question come through. Have you got any dates for when the units, some other units in China will be commissioned? Yes, if you look into my report, there it roughly says when in this year some of the units will be commissioned. A lot of them said earlier in the year. However, this hasn't been the case. For example, Guodian Taizhou was supposed to be early 2015. It's now August and in the first stage of commissioning, so I think they're running a bit later than expected. And then the report details some later commissioning, and there's also one unit as described in 2017 which will be commissioned. So yeah, hopefully by the end of this year we should have the majority of the Chinese double reheat units commissioned. I'll just wait for maybe some other questions. And also, if you do have any questions after the webinar, please feel free to give me an email. My email's on this slide, and I'll get back to you as soon as I can. And whilst I'm waiting, the slides for this webinar will be made available in the near future for download from this website. And also, we have another webinar in a month, which will be by Anne Carpenter, and is titled Water Availability and Policies for the Coal Power Sector. Okay, there have been no further questions. So if there are any more questions, just please email me, and I'll be happy to get back to you. Right, okay, thank you very much for listening, and speak again. Bye-bye.